Classifying unstructured clinical notes via automatic weak supervision. This presentation describes an attempt to reproduce the results presented in the paper by Gao et al. 2020, titled Classifying Unstructured Clinical Notes via Automatic Weak Supervision, which was published in the Proceedings of the 2020 Conference on Empirical Methods in Natural Language Processing. My focus is on classifying unstructured clinical notes using automatic weak supervision. I'll provide an overview of the paper's methodology and results and present my own findings from attempting to reproduce their results. Why is this topic important? This work is important for healthcare because it addresses the need for reliable automated classification of unstructured clinical notes, which is a challenging and time-consuming task. This proposal provides a potential remedy to this challenge by enabling the quick and affordable development and deployment of effective text classifiers while assigning diagnostic codes to unstructured clinical notes. By improving the accuracy of diagnostic code assignment, author's proposal can reduce the risk of billing and coding errors, which can lead to financial loss and federal penalties for healthcare providers. Labeling a discharge summary note with the corresponding ICD-9 code is a challenging task that requires expertise of a domain expert. You can see below example of a discharge summary note. This note was taken from a Mimic3 database. So what is the proposal? The paper introduces a weakly supervised text classification framework called KeyClass. KeyClass combines data programming with a method for automatically acquiring interpretable weak supervision sources from class-labeled descriptions. KeyClass aims to efficiently and effectively create text classifiers that can assign diagnostic codes to unstructured clinical notes with minimal human effort and without vast quantities of labeling training data. The following diagram illustrates two data labeling methodologies, full supervision and weak supervision. Full supervision requires a subject matter expert to manually label each data point, including clinical notes in our case. In contrast, weak supervision utilizes a systematic probabilistic approach for labeling each data point. For our project, we employed a label model to annotate our datasets relying solely on this weak supervision technique. So let's go into more details on author's proposals. So first, we employ data mining techniques to develop a collection of classes and corresponding descriptions for each top-level ICD-9 code. We also extract a group of frequently occurring keywords from the text corpus, which consists of discharge notes. Next, we utilize a Bluebird model and encode class descriptions and keywords. Next, we create a label model that generates label functions, assigning a class to each keyword through a voting system. We apply the label model to annotate the datasets. So once we have our probabilistic labels, we're able to train our classifier on probabilistically labeled dataset. So looking a little bit closer into that classifier, the structure of the model is essentially is 4 layers, linear layers, and also the ReLU activation layers. We're using our criterion is cross entropy loss, and the optimizer is the atom optimizer. The next step is to then employ the self-train mechanism, and the model is the same model, and the criterion is KL div loss, and the optimizer is the same atom. As part of the reproduction work, I was attempting to demonstrate that KeyClass performs on par with the fully supervised baseline FastTech Venkataraman et al. On the Mimic3 ICD-9 code assignment problem. I was unable to achieve the expected accuracy scores. The expected accuracy score was close to 67, but the actual accuracy score achieved was only 16, with a standard deviation of 0.0026. Additionally, the precision and recalls were also significantly lower than expected. For the same reason, I also failed to demonstrate the superior performance of weakly supervised KeyClass 6252 over its FastTech counterpart 0.525. The expected accuracy was close to 0.62. That was the expectations from what the authors were able to achieve. I was unable to replicate the results that the authors claimed in their paper. My hypothesis for this is as follows. The blue highlighted step in the workflow requires extensive data mining since there is no mapping between the class and its descriptions. And the authors did not really go into detail explaining how they generated this mapping. My hypothesis for the failure is that the logic used to produce the class description from low-level ICD-9 descriptions may not have been distinctive enough, leading to a low accuracy score in the red highlighted step. In other words, my accuracy score, as a result of applying the labeling functions, was very low. It was about 30%. Essentially, then it turned this whole problem into garbage in and garbage out. I think that's the reason why my experiment failed.